Welcome back to the session on Fourier transforms. In the previous session, we discussed the Fourier transform of a function f of t. That is, Fourier transform of a function f of t is defined as this is a function of omega and is defined as integral from minus infinity to infinity f of t into e raised to minus I omega t dt. If f of t is an even function, then the Fourier transform is 2 times integral from 0 to infinity f of t into cos omega t dt. And if f of t is an odd function, then the definition will become Fourier transform of f of t is equal to minus 2i into integral from 0 to infinity f of t into sin omega t dt. All these definitions are discussed in the previous session. In this session, we shall discuss the Fourier transform of some elementary functions. First one is the unit step function. Unit step function is defined as u of t is equal to 0 for t less than 0 and u of t equal to 1 for t greater than 0. Then the Fourier transform is integral from minus infinity to infinity f of t into e raised to minus I omega t dt. That is equal to, we have to split this integral, that is integral from minus infinity to 0 f of t into e raised to minus I omega t dt plus integral from 0 to infinity f of t into e raised to minus I omega t dt. Here f of t means the function is unit step function. Therefore, we can replace f by u. This also f of t means u of t. In this first integral, u of t is defined as 0 because t is less than 0. Minus infinity to 0 means t is less than 0. Therefore, 0 plus. Here in this case, integral from 0 to infinity means t is greater than 0, in which case u of t is defined as 1. Therefore, integral from 0 to infinity e raised to minus I omega t dt. On integration we get e raised to minus I omega t divided by minus I omega between the limits 0 and infinity. That is e raised to minus infinity minus e raised to 0 divided by minus I omega. E raised to minus infinity means this is tends to 0 minus e raised to 0 is 1 divided by minus I omega, that is 1 by I omega. Now consider the function f of t is equal to e raised to minus a into modulus of t. We want to find the Fourier transform of this function. By definition, the Fourier transform is Fourier transform of f of t is equal to integral from 0 to infinity f of t into e raised to minus I omega t dt. Here it is clear that this function is an even function. If f of t is even, then the definition will become Fourier transform of f of t is equal to 2 times integral from 0 to infinity f of t into cos omega t dt. Here the limit of integration is minus infinity to plus infinity. If f of t is an odd function, then the Fourier transform is minus 2i into integral from 0 to infinity f of t into sin omega t dt. In this function, this is an even function. Therefore, Fourier transform is 2 times integral from 0 to infinity f of t is e raised to minus a into mod t cos omega t dt. Here we can write this equal to 2 into integral from 0 to infinity. In this range, that is t is from 0 to infinity, modulus of t is t itself. Therefore, this is equal to 2 times integral from 0 to infinity e raised to minus a t into cos omega t dt. That is equal to 2 times integral from 0 to infinity e raised to minus a t into cos omega t can be written as the real part of e raised to I omega t, because e raised to I omega t is equal to cos omega t plus I into sin omega t. That means cos omega t is the real part of e raised to I omega t dt. That is 2 times real part of integral from 0 to infinity e raised to, here we can write minus t into a minus I omega dt. On integration, we get 2 into real part of e raised to minus of a minus I omega t divided by minus of a minus I omega between the limits 0 and infinity. Applying the limits, we get this equal to 2 into real part of, when we apply this upper limit, e raised to this tends, the numerator tends to e raised to minus infinity, that is tends to 0, minus, when t equal to 0, this is e raised to 0, that is 1, divided by minus of a minus I omega. That is equal to 2 times real part of 1 divided by a minus I omega. That is equal to 2 times real part of, we have to multiply the conjugate of a minus I omega both in the numerator and denominator. We get a plus I omega divided by, in the denominator, a plus I omega into a minus I omega means a square minus I omega square. That is 2 times real part of a plus I omega divided by a square plus omega square. Because I square is minus 1, we will get in the denominator a square plus omega square. This is equal to 2 times here real part of a by a square plus omega square plus I into omega divided by a square plus omega square. That is 2 into real part is a by a square plus omega square. That means the Fourier transform of e raised to minus a into mod t is 2a divided by a square plus omega square. Now consider the function f of t is equal to mod t into e raised to minus a into mod t. We have to find the Fourier transform of this function mod t into e raised to minus a into mod t. Clearly, this is an even function because mod t is even. Here also mod t, therefore, these two are even functions, and the given function is a product of two even functions, which is again an even function. Therefore, by the definition, the Fourier transform is Fourier transform of f of t is equal to 2 times integral from 0 to infinity f of t into cos omega t dt. That is, here f of t is mod t into e raised to minus a into mod t cos omega t dt. In this range, that is, t is from 0 to infinity, the modulus of t is t itself. Therefore, we can write this is equal to 2 times integral from 0 to infinity t into e raised to minus a t into cos omega t dt. Now, we have to evaluate this integral from 0 to infinity t into e raised to minus a t cos omega t dt. Consider the integral from 0 to infinity t into e raised to minus a t into cos omega t dt. We know that integral from 0 to infinity e raised to minus a t cos omega t dt is equal to integral from 0 to infinity e raised to minus a t into, here cos omega t can be written as real part of e raised to I omega t dt. That is, real part of integral from 0 to infinity e raised to minus of t into a minus I omega dt. One integration will get real part of e raised to minus of a minus I omega t divided by minus of a minus I omega. This is equal to limits are 0 to infinity. When t tends to infinity, this will become 0, that is real part of 0 minus e raised to 0 is 1 divided by negative of a minus I omega. That is equal to real part of 1 divided by a minus I omega. Multiplying both numerator and denominator by conjugate of a minus I omega, we get real part of a plus I omega divided by a square plus omega square, and the corresponding real part is a by a square plus omega square. That is, this integral from 0 to infinity e raised to minus a t cos omega t dt is a divided by a square plus omega square. Now, differentiating both sides of this expression with respect to a, we get d by dA of integral 0 to infinity e raised to minus at into cos omega t dt is equal to d by dA of the right hand side is a divided by a square plus omega square. That is here we can write this as integral from 0 to infinity cos omega t into d by dA of e raised to minus at dt is equal to, here the derivative is in the denominator a square plus omega square the whole square, and in the numerator this is a square plus omega square into derivative of a is 1 minus a into derivative of a square is 2a. That is here integral from 0 to infinity cos omega t into derivative of e raised to minus at is with respect to a is e raised to minus at into minus t, because the differentiation is with respect to a, the coefficient of a is minus t dt is equal to, the right hand side is a square plus omega square minus 2a square means a square minus 2a square is minus a square, that is omega square minus a square all divided by a square plus omega square the whole square. That is integral from 0 to infinity minus t into e raised to minus at cos omega t dt. Is equal to omega square minus a square divided by a square plus omega square the whole square. That is integral from 0 to infinity. If we multiply both sides by minus 1, we get integral from 0 to infinity t into e raised to minus at into cos omega t dt is equal to a square minus omega square divided by a square plus omega square the whole square. Therefore, the required Fourier transform is that is the Fourier transform of mod t into e raised to minus a mod t. Since this is an even function, the definition will become 2 times integral from 0 to t into e raised to minus at into cos omega t dt. In this range 0 to infinity modulus of t is t itself. Therefore, we can write this expression as 2 times integral from 0 to infinity t into e raised to minus a into t cos omega t dt. The value of this integral is a square minus omega square divided by a square plus omega square the whole square. Therefore, this is equal to 2 into a square minus omega square divided by a square plus omega square the whole square, which is the required Fourier transform of the given function mod t into e raised to minus a mod t. Now consider another function f of t equal to 1 by t into e raised to minus a into mod t. We want to find the Fourier transform of this function 1 by t into e raised to minus a into mod t. Here 1 by t is an odd function, e raised to minus a into mod t is an even function. Therefore, a product of odd function and even function means this is an odd function. This product is an odd function, that is the given function is an odd function. Therefore, the Fourier transform is this. Here Fourier transform of f of t equal to minus 2i into integral from 0 to infinity. F of t is this 1 by t into e raised to minus a into mod t means t in this range 0 to infinity into sin omega t dt. We denote this by f of omega, that is f of omega is minus 2i into integral from 0 to infinity 1 by t into e raised to minus a t into sin omega t dt. Now, differentiating with respect to omega, we get f dash of omega is equal to minus 2i into integral from 0 to infinity 1 by t is a constant because the differentiation is with respect to omega. E raised to minus a t is also a constant. Here derivative of sin omega t is cos omega t into t, because the differentiation is with respect to omega means derivative is cos omega t into coefficient of omega is t dt. This t and t will be cancelled. This is equal to minus 2i into integral from 0 to infinity e raised to minus a t into cos omega t dt. This is equal to minus 2i into, here the value of this integral is, as in the previous problem, it is a by a square plus omega square. This f dash of omega. Now, integrating with respect to omega on both sides, we get f of omega as minus 2i is a constant. Therefore, f of omega equal to minus 2i into integral a by a square plus omega square d omega. That is equal to minus 2i into integral a by a square plus omega square d omega is tan inverse omega by a plus constant of integration. Now, f of omega equal to minus 2i into integral from 0 to infinity 1 by t raised to minus a t into sin omega t dt. If we substitute omega equal to 0, we get f of 0 as, when omega equal to 0, this sin omega t will become sin 0. Sin 0 is 0. Therefore, f of 0 equal to minus 2i into 0 means 0. From here, we get f of 0 equal to minus 2i into tan inverse 0 by a. Tan inverse 0 by a means tan inverse 0. Tan inverse 0 is 0. Therefore, here from here we will get f of 0 equal to minus 2i into 0 plus c means f of 0 equal to c. From these two we can write c equal to 0. Therefore, f of omega equal to minus 2i into tan inverse omega by a plus 0, that is minus 2i into tan inverse omega by a, which is the Fourier transform of the given function 1 by t into e raised to minus a into mod t. So, consider one more function. F of t is equal to e raised to minus a t into signum t. E raised to minus a into mod t into signum t. The signum function is defined as signum of t equal to minus 1 for t less than 0, and this is equal to 1 for t greater than 0. The graph is like this, minus 1 is here. Therefore, for t less than 0, graph is towards the left, and for t greater than 0, graph is a constant, a straight line parallel to positive horizontal axis. From this graph, it is clear that the signum function is an odd function. Here, e raised to minus a into mod t is clearly this is an even function. Signum function is an odd function. Therefore, this is a product of an even function and odd function, which is an odd function. Therefore, the Fourier transform is minus 2i into integral from 0 to infinity f of t is e raised to minus a into, we can write t for mod t, because the variation of t is from 0 to infinity into signum of t sin omega t dt. This is equal to minus 2i into integral from 0 to infinity. Signum t is defined as minus 1 for t less than 0 and 1 for t greater than 0. Therefore, e raised to minus a t into signum of t is defined as minus e raised to a t for t less than 0 and e raised to minus a t for t greater than 0. Therefore, we can write here integral from 0 to infinity. 0 to infinity means t greater than 0. E raised to minus a t into signum t is e raised to minus a t into sin omega t dt. This is equal to minus 2i into integral from 0 to infinity e raised to minus a t into, we can write sin omega t as the imaginary part of e raised to I omega t dt. This is equal to minus 2i into imaginary part of integral from 0 to infinity e raised to minus of t into a minus I omega dt. That is minus 2I into imaginary part of one integration will get integral 0 to infinity e raised to minus of a minus I omega t dt is e raised to minus of a minus I omega t divided by minus of a minus I omega between the limits 0 and infinity. This is equal to minus 2I into imaginary part of when t equal to infinity, this numerator tends to 0 because e raised to minus infinity tends to 0, minus when t equal to 0, the numerator will become 1 divided by minus of a minus I omega, that is equal to minus 2I into imaginary part of 1 divided by a minus I omega, that is minus 2I into imaginary part of, we have to multiply both numerator and denominator by a plus I omega, we get a plus I omega divided by, here a plus I omega into a minus I omega means a square minus I omega square, that is a square plus omega square, which is equal to minus 2I into imaginary part of a by a square plus omega square plus I into omega by a square plus omega square, that is minus 2I into, from here imaginary part is this omega by a square plus omega square, that is minus 2I omega divided by a square plus omega square, which is the required Fourier transform of the given function e raised to minus a into mod t into signum t. With this example, let me conclude this session. Thank you for watching this class. Have a nice day.